Our next speaker is Dr. Krepel. I think everybody already knows who he is. He's spoken yesterday. He's, just to remind everyone, he's responsible at PSI for advanced reactors of fuel cycle analysis. And he's going to give us a talk about the SAMOFAR, which is a paradigm shift in reactor safety with the molten salt fast reactor.
Thank you very much, Mr. Chairman. I have the privilege to present some of our project here. It's mainly because all my other colleagues are probably in Oak Ridge. And it's a coordinated project financed by European Union. The coordinator is Jan Len Klosterman from TU Delft, Netherlands. We are one of the participants, Paul Scherrer Institute. The other participants are like 10 institutions from European Union and one partner from Mexico. The main aim, the grand objective of some of our project is to prove the innovative safety concept of molten salt fast reactor and to deliver some breakthrough in nuclear safety and waste management. A secondary aim is to create kind of consortium of stakeholders to assure kind of continuation of the MSFR project beyond SAMOFAR. And the expected result is a proof of concept. It's a safety assessment of MSFR and also updating conceptual design and a kind of roadmap for momentum among the stakeholders. SAMOFAR is organized as many other European projects. So you have a European Commission, which is more or less paying the money, project coordinator, it's Jan Lien. Then you have a governing council. This is one representative from each institution, and project management board, where there are the working package leaders and coordinator. They are in touch with advisory board, so we have several respected scientists in the advisory board, and we are also kind of exchanging information with Generation 4 MSR steering committee and with observer and non-European project. So one of the first observer, which we will probably soon approve, is the ThEC15, NRG pattern. They are irradiating samples with lithium thorium salt, so it's very highly interesting to have them in the project. But there may be other institutions interesting to become observer. There are 7 working packages. Working package 7 is for management of the project, working package 6 for insemination, and 5 technical work packages. Okay, it takes some time probably now. Okay, so here you can see the leaders of the work packages. So working package 1 for integral safety is Elsa Merle-Lucot from CNRS France. More or less, this is the institution which developed the MSFR in the previous EVOL project. Ondřej Beneš, a very known expert from ITU Karlsruhe, responsible for WP2, which is about chemical properties, safety relevant properties of the salt. Marco Ricotti from CIRTEN, it is a consortium of Italian universities, so he's from Politecnica di Milano in Italy. They should look on decay heat removal systems. Danny Ladhovers from TU Delft in WP4, it's a multi-physics simulation. And Sylvia Delpech, which is for a long time representing the reprocessing issues and chemistry of the molten salt reactor. The working package 6 is dissemination, and working package 7 is more or less management. Concerning the non-European partners, some of our project proposal was recommended to the European Commission by Shanghai Institute in Applied Physics. We hope to cooperate with them later on also, with Kurchatov Institute from Russia. They are applying for a research grant of SMART, which is connected to MSFR, so probably there will be also like first or second partner to sign agreement to cooperate on this project. And then also University of New Mexico which is executing this fast, big project for fluoride salt-cooled high-temperature reactor. Now, let me just shortly introduce the working packages. So the working package 1, led by CNRS France, is about integral safety assessment. There are several foreseen tasks. One of them is development of power plant simulator, looking on dynamics behavior of the molten salt fast reactor, including the startup and shutdown procedure, controlling and load float operation. There is always discussion about this reactor, if you need control rods or not. And I don't have a clear answer if you need control rods or not. But there is also another discussion if you need shutdown rods. And somebody claimed you don't need shutdown rods because you just drain the core. Probably if you would have here IAEA experts, they will say it's not enough. You need to shut down the reactor other way. The aim is mainly to develop integral safety assessment methodology. And it should be based on, so the assessment should be done by integral safety, and looking on proliferation aspects. So for instance, PSI has a task in this working package, and we plan to look on simplify PSA level 3 simulation. So simulating something like big early release and looking how the source time may spread if you compare it to light water reactors. The reference design will be adopted from EVOL project. So you may have already seen in some publications this core, but we know that it's kind of academic vision. It needs to be optimized, definitely. And you can see the parameters of the core is very high power for very small salt content. Somewhere it should be, yes, 18 cubic meters in a whole primary circuit. So it's really challenging design, and probably it may be slightly changed, increase the volume if necessary. The reference startup salt at the moment is composition of enriched lithium fluoride, thorium and uranium fluorides with transuranics. There were some discussions and issue how it should be the first mixture, and there were different positions. For instance, the reprocessing working package was or opposing that if you use just only for instance plutonium with thorium or too much uranium, you can have issues in the reprocessing stream. So this is at the moment the compromise, but probably we will once again look on it. There are 16 loops, 16 heat exchangers, and they are next to the reactor. I'm sure that the working package 3, which should look on decay heat, will immediately propose to place them above the core. You have also this kind of first visualization how it can look, where the barriers can be, but it is also far from reality. So those are the tasks we also plan to address. In WP2, safety-related data, it is planned to prepare synthesis salt, so lithium fluoride salt with plutonium and uranium, and to measure phase diagram of it and develop some new experimental techniques for thermal properties of the fuel salt. And very interesting tasks there are the examination by supercooling. So what happens, what components of the salt precipitate as first. And on the other hand, if you overheat the salt, what happens with the partial pressure of different components, so what is coming out of the salt. And especially, the last point now, especially looking also on iodine and cesium behavior properties in the salt. There is also a plan for experiment of salt-water interaction under, let's say, irradiation conditions or ionization conditions. There is example for the cesium and iodine behavior, and you can see there will be 3 different cases addressed, and it should be more or less done at ITU, but also the chemistry and redox potential will be done in France, in CNRS Toulouse. In working package 3, where the Politecnico di Milano is the leader, It's planned to use former solar salt facility. There is already existing loop for solar salts, nitrite salt, and we would like to simulate the decay heat removal with natural circulation for volumetrically heated liquid. So more or less there will be a salt loop which will be heated on along the pipe, and only on one place there will be cooler, so heat exchanger. And the aim is to check the natural circulation and to create the kind of stability maps for the volumetrically heated liquid. What will be not addressed, which is another interesting issue of volumetrically heated liquids, is the heat exchange correlation between the volumetrically heated liquid and solid surface. So this is not the aim of this project, because this will be heated from outside. Also, the draining and freeze plug should be studied here. So in CNRS Grenoble, they plan to install a facility where they will be really looking on the behavior of the freezing plug. But in this case, it's foreseen to use a kind of metallic plate as a main plug, and only small layer of salt in between the tube and the plate, which should be molten, so that once the small layer is molten, the plate will fall down and open a very big pipe for draining, because it should be done relatively quickly. Yeah, and also it's planned to do some measurement of solidification phenomena along the walls. WP4 is a numerical assessment. We plan to use really like multi-physics cutting-edge tools. For instance, like open foam-based CFD coupled with Serpent, or at PSI we have just diffusion on unstructured mesh with coarse mesh or fine mesh thermohydraulics. And based on the input from WP1, we should simulate the selected transient of MSFR, check the decay heat removal via natural circulation, and for instance, we plan at PSI to look on thermal expansion of the reactor vessel, because we can deform the mesh in our solver, in our GenForm solver. So we plan to look on vessel expansion and the impact on reactivity. And also what we plan to look on is on freezing of salt in subsection. Assuming, for instance, that you are undercooling the salt in heat exchanger, you may come to a situation where you block it. So the main aim here is not to establish the method for reprocessing, but to look on a safety of the existing reprocessing scheme from EVOL project, and the interaction between a chemical plant and the reactor and vice versa. Evaluation of radioactive and chemical toxic gas stream and solids and fluid product stream. One of the part is also shielding and hold-up tanks, sizing, and for instance also evaluation of the liners. This is the contribution of the Mexican partner, and the impact on chemistry and material behavior. The reprocessing scheme has several steps. The one of the last step, the reduction extraction, is also kind of expected outcome of this project. We would like to verify that it works. The WP6 dissemination is more or less the last working package if you don't account for the project management. And we plan, there will be many students involved in this project. We plan to exchange these students between the institution, make some probably summer school for students, but also compilation of strategic stakeholders and workshop for workshop. So we really want at the end of SummerFAR to have clear vision if there are some industrial or commercial partners interested in this reactor, and to be sure that it has sense to continue in Europe doing this research. Yeah, so that's more or less all from my side. Thank you for your attention.
Thank you, Dr. Krepel. And we'll open the floor for some questions. Yes, Dr. Rebel.
For my information, how long do you think you need to open the drain in MSR? Because depending on what kind of reactivity insertion you make, it takes a few 5-6 milliseconds to increase the power by 2 orders of magnitude. So can you do it as fast enough?
Okay, that's a very relevant question. I will start the answer with saying that I'm not sure that draining is the best method. You may maybe think about in-vessel retention or designing the primary circuit so that there is at the bottom of the circuit kind of draining tanks, but integral part of the primary circuit. But to answer your question, we don't have moderator, we don't have graphite. And graphite provides you thermal inertia, so you can be much slower with draining this core, even though you should relatively hurry. In our case, the criticality issue is not there. You have negative feedback, so the salt will heat up, the chain reaction will be stopped. But still, there will be decay heat heating up the salt, so you should manage to drain the core relatively fast. So for the opening itself, how fast it should take, it can be seconds. But the question is, how big should be the pipe to drain these 18 cubic meters? And then there we may speak about, I don't know, 20, 30 seconds. That's the aim of the simulation, to find out probably how many valves you need, or how big should be the diameter of the pipe. Another thing they want to look on is the idea now is that you reach the criticality by pumping the salt back to the core, which may be problematic. Because you may pump in a cold salt, which may become critical, heat up, and so on. So I guess what we should clearly know after or in between of this project is that there should be kind of independent shutdown system. You need always 2 shutdown systems. So although the startup may be not yet developed well, but it's clear that since we don't have this thermal inertia, we should do it very fast. Yes, faster than the thermal system. Yes.
I see. You have gone to 2 other countries, I think, other than the European countries, that is China and Russia. Any other country outside this EU? You saw it in the slide.
In our consortium, there is already one partner from Mexico. Russia is traditional partner. There was already 2 projects.
In one of your slides, you had shown some countries in the beginning.
Yeah.
Next slide.
Yes, but
other countries' projects.
Somehow this slide is problematic. So let me try to go like this. Yes.
Yeah, here. China, Russia, USA. Am I right?
Yes.
Non-EU projects.
Yes.
So did you consider India as one of the things? That's my first question.
Let's say this. We are very open. For cooperation. We also plan to publish more or less all the results in open journals. If it is just one way, that you just want to be observer, it's also acceptable. But at best, is if you have some interesting niche or some of your results to share, then it's the best. So we have already now like more than 3 applications for observers, and it's a purely decision of the governing council. So as a member of the governing council, I would be glad to see contributions from India.
Thank you for this positive answer. If you go to the aim of your project, some of our aim.
What is the aim of your project? It's like slide number 3.
1. 2. Yeah. To prove the innovative safety concepts of MFSR, deliver breakthrough in nuclear safety and waste management.
Yes.
So that means when you set out to set this aim of MFR, so did you conclude in advance that there is no safety and waste management ab initio when we talk of MSR? Was that the reason to go in for MFR?
No.
Because your aim is speaking like that, so it is a cause of worry for anybody who's pursuing MSR as a country. Will get worried that means there is safety concern in MSR. And that's why you set out for this project, very ambitious, wonderful project.
Yes. So basically, you could have heard today and yesterday that many MSR systems think about draining tanks and freezing valve. Yes, so we really want to simulate it, to do an experiment, if it works and how fast it works. Yes, because, for instance, 1 hour or 2 hours ago, we saw a system where there was a small pipe for draining of the salt. It will take several minutes to drain the core. So we would like to look on it experimentally, really. So that's if you speak about neutronics, in the last project, they were trying to make the reactor super prompt critical with inserting reactivity, but not promptly. There was some ramp of inserting the reactivity. And firstly, by 6,000 PCM, it was prompt critical, because the feedback, thanks to the salt expansion, is propagating with sound speed. So you need a huge reactivity to make it prompt critical.
Yeah, you're right, but your work packages, if you relook, then it covers the whole spectrum of the activity. It is not only just for that small thing which you're saying about draining. So that means overall there is a concern in the safety of MSR. That's what I'm saying. Your work packages, what you showed, covers the entire spectrum.
Yes, of course.
No, which is a good thing.
There are different perspectives on the safety.
Yeah.
For me, for instance, the iodine and cesium behavior of the salt will be probably more relevant to the safety than freezing valve.
Yeah, chemistry. You have a package of chemistry.
Yes. Very strong package on chemistry. Yes.
Thank you.
Okay, thank you. I guess you could continue that offline. Let's have the question from.
Technical question. The work package 4, who's undertaking this neutronic assessment, and which are the toolings that are used? Are software that is specially developed for this MSR concept? And the second question that is also related to what the gentleman was saying before, the non-European countries are beneficiary of the project, which means they can access to some funding, or are just collaborating institutes that can take part to the project, collaborate, but not get access to funding?
So I will answer the second question first. Probably it's too late to get some funding, because the project is already financed by European Commission. So it would be great having partner from non-EU country before submitting the project, like we have the Mexico. Now, if you want to become a partner or observer, it means if you would like to get some money, means you must reduce our own work somehow. So typically you must have your own project, you must have your own interest if you want to join. And for instance, NRG will provide the results about the salt irradiation, which is excellent. So we will surely accept them as an observer. The same is with Russians. So you must more or less come with something, yes? So you must have your own budget.
But in principle, they could have access to the funding. They could be beneficiary of the European project.
If it would be, I think so, like the Mexico. You must have your own funding, you must promise your own work, and then if you share this work with the others share the work with you. So it's possible. Okay. And the first question for the tools, more or less, there will be 3 institutions, all using open foam-based tools, slightly different tools, and it's a field solver for multiphysics. So in our case, you have 3 independent meshes for thermal expansion, for thermohydraulics, and for neutronics. And even though it's only diffusion, for molten salt reactor it doesn't matter so much, you can deform the mesh, which is something which you cannot find in many codes. The typical nuclear codes, you can expand the reactor in radial or axial direction equally for all assemblies. Yes, but we can expand it according to the deformation of the vessel, following the real temperature field. So it will be mainly multiphysics tools, especially developed for MSR, so including this daily neutron drift. And depends to what level of detail you want to go. You may also simulate the decay heat, because the decay heat will be also a function of position in the primary circuit to a certain extent.
Okay, thank you. Let's give the gentleman an opportunity.
Bill Nuttall from the Open University. I'd like to take it back to the question of why the emphasis on safety, and invite Yuri to chip in later if he disagrees with what I'm about to say. So the earlier questioner said, is this emphasis on safety because there's a special technical concern about safety in the MSR and in Samafar? And I think the answer to that is no. There is no special concern about safety. I think the reason that there might be an emphasis on safety is there's a special aspect to research policy, that this is a Euratom fission-funded project, and the Euratom Treaty requires all 28 member states to agree on essentially anything that is done, and safety is an uncontroversial virtue. And there is complete comfort in working on the safety of nuclear systems, and this is a project working on the safety of nuclear systems.
Yeah, okay, I don't know if politically correct, but the right answer is that you should look on the Horizon 2020 call, what was the European Commission calling for. And if you go through this proposal, you cannot find many areas where you can apply for molten salt reactor project. But one area was innovative safety. Yes, so the EC was calling for innovative safety. And we know that MSR has innovative safety features, so we put the project in that position. And there was a requirement that you should bring several systems from technological readiness level 2 to technological readiness level 3. So we selected several cases like the liquid metal reduction or the freezing plug or the decay heat removal with volumetrically heated liquid, that we will really bring it from technological level readiness 2 to level 3. So there was also the boundaries where we try to fit in. Yes, yes.
All right, one more question.
Okay. Can you please give an outline of what activities do you plan in your project for development of materials and qualification as per code?
Can you repeat once again? Materials?
Structural materials and development of structural materials for high temperature use in molten salt environment for this MSFR reactor, which is a reference design, and its code validation. What efforts are being planned?
So as you know, if you use lithium thorium salt, you have relatively high melting point, like 560 degrees C. And if you have fast reactor, the wall, presumably from Hastelloy, will be relatively strongly irradiated, so and relatively also very hot. So one of the tasks we have there is using these liners, so using I think zirconium oxide or something like this liner, so that you will more or less isolate the wall, assuming that behind the wall you have colder salt, so that the material will be colder. But we plan to rely on Hastelloy, modify Hastelloy N, and it's very probable that you will need to replace it quite often. Yeah. So we don't plan any irradiation or chemical test of Hastelloy. I think since anyway we will need to replace it, that's fine for that project. And the other question?
Code validation aspect?
What aspect?
Hastelloy has to be validated for use for nuclear applications.
Hastelloy was the material used during the MSRE experiment, so I think so.
No, but the MSRE was designed as per Section 8 boiler vessels code. You cannot design reactors by Section 8 now.
Sorry, there was no thorium in the MSRE, or what you said?
In MSRE reactor was designed by as per Section 8 of ASME boiler and pressure vessel code. And
I have problems to understand you. Maybe we can discuss between us then.
Yes, I think that's a discussion that can be taken separately offline. With that, I'd like to thank Dr. Krepel very much for his presentation. It was very entertaining, very enlightening. Thank you.
Yes.